Hi, this video introduces infinite series, and we're going to be talking about infinite series for the rest of this chapter. Here we're essentially going to learn the main idea and a couple of quick examples. Before I give this definition, let's actually roll out an example. So suppose I have the summation as k goes from 1 to infinity, that's an implied positive infinity, of 1 over 2 to the k. So this means 1/2 plus 1/4 plus 1/8 plus 1/16, etc. But what does it actually mean to add up infinitely many things? You have never literally added infinitely many things. Addition is done in finite situations. So we need to make sure we actually understand what this means, because otherwise we're just memorizing rules or manipulating symbols. This has a meaning, and if you understand its meaning, some of the things we do with it will become much clearer. So here's what I'm going to do. I'm going to imagine a running total. Let's say I'm not adding infinitely many things. I'm adding finitely many things. So if I stop after the first one, my running total is 1/2. If I stop after the second one, I have 1/2 plus 1/4, which is 3/4. If I stop after 1/8, my running total is 7/8. My next running total is 15 over 16. My next running total is 31 over 32, then 63 over 64, etc. So now, what I'm actually focusing on is just this sequence of numbers. I don't really need to think about where they came from. I don't really need to think about addition. I'm just looking at 1/2, 3/4, 7/8, 15 16, 31 over 32. And I'm noticing that they're getting closer and closer to 1. So we're going to take that as the definition of what we actually mean to add these things together. It is the limit of those running totals. Those running totals are more formally called partial sums. It's kind of like when we did improper integrals. We're not literally allowed to plug in infinity. Instead, we stop somewhere, calculate our answer, and ask what's the limit of all those finite things. So a series, sometimes we say infinite series just to emphasize that, but by default they are infinite. What this is, by definition, is we add together, oh, there's a typo here. This should be a sub k. We add together the first n terms. And then we run a limit on those partial sums. So if the running totals are getting closer and closer and closer to some specific number, by definition, we say that that is the sum of the series. So we can talk about the sum, and we can say the series converges. So the series converges if that limit of partial sums, if that sequence of partial sums has a limit. Otherwise, we say the series diverges. So we're taking what we know about sequences and using them to understand this idea of infinite addition, because infinite addition gives us a sequence of numbers. So we are going to spend a lot of time learning some rules to help us figure out, when do things like this actually have an answer? When is it possible to add together an infinite list of numbers, and when is it impossible? So we're going to just look at two basic ideas. So let's think about a geometric series. I'll remind you, a geometric series is one where we're always multiplying by the same amount. So for this one, I started with 4 and times 3, times 3, times 3. Now, what if I wanted to add these together? So here, this is the more abstract version. Can I add these together? Well, let's just look at this. My running totals are 4, then 16, then 52, then 160. Because the terms are getting bigger and bigger, obviously those running totals are getting bigger and bigger. They're not approaching anything. So it's pretty clear that if r is at least 1 in absolute value, here we're just imagining positive examples, but it's the same with negative, the partial sums keep getting bigger and bigger and bigger, so it definitely diverges. Oh, and another typo here. Right, this should just be greater than or equal to. When r is greater than or equal to 1 in absolute value, we have a divergent geometric series. Now, what if it's smaller than 1? And I'm just going to assume it's positive for simplicity. So here is a fact of algebra. If we take this partial sum, just as a fact of algebra, I can tell you that it is equal to this. Now, regardless of what n is, we know that this is a positive number and this is less than 1. So this whole thing is less than 1 over 1 minus r. So all of the partial sums are smaller than some particular number. And remember, that means they're bounded. So all of my running totals are smaller than this number, whatever that is, right? I'm being general, I'm not saying what r is. If r, for example, was 3/4, then this number would be 4. So if we're doing that, if our number is 3/4, then we can say all of those partial sums are less than 4. So they're not growing infinitely big, but they are growing. So those partial sums are increasing and bounded. And we had a theorem that says if we have a sequence that is monotone and bounded, it does have a limit. So that's the first thing we've noticed here. If we're adding these up and r is less than 1, there definitely will be a limit to those partial sums. There definitely will be a total. Now let's use algebra to solve for the sum. Yeah, so here's what I'm going to do. I'm going to do, you could use this formula that I have up here, but here's another little algebraic trick. So let's just take this thing, a plus ar plus ar squared plus ar cubed, etc. This is an infinite geometric series. And let's just say that that's equal to t for total. So what I'm going to do is I am going to subtract a from each side. So if I subtract a from each side, I have r, ar squared, ar cubed, etc. It goes on forever. And I'll just say t minus a over here. Now, what we'll notice is that this thing that I got from subtracting is actually the same as r, right? Now, every single term here has an r. I'm going to factor it out. So it's r times a plus ar squared, etc. But this is the same as what we started with, and we called that t. So what we have here is that r times t is equal to t minus a. So that's equivalent to saying a is equal to t minus t times r, which is t times 1 minus r. And that total is a over 1 minus r. So here's our geometric series formula. If r is less than 1 in absolute value, I assumed positive so far, it's similar if it's negative. This generic geometric series, so this is the summation as k goes from 1 to infinity of a times r to the k minus 1. because I actually want to start with 0 copies of r. This is equal to a over 1 minus r. A is the first term. R is the common ratio. And you should just know this. You don't want to have to figure it out. If you're noticing you have a convergent geometric series, then apply this formula. Now, one thing I want to point out is I figured out the formula by doing algebra, but you should only attempt to solve for a sum after you've established that it's convergent. If you try to do this with something that is divergent in the first place, you'll get an absurd answer. So let me just show you at the very end. Don't try to figure stuff out until you know it converges. So let's imagine this. 1 plus 2 plus 4 plus 8. I'm just adding consecutive powers of 2. Now that obviously diverges. Those numbers are getting bigger and bigger and bigger. We are not getting a number here. But let's pretend this is true and do algebra. So what if I double both of these? I would have 2 times 4, 2 plus 4 plus 8 plus 16 plus 32 equals 2 times s. Now I'm going to add 1 to each side. We will notice that what we have here is actually the same as what we started with. I doubled it and added 1, and I got what I started with. So this is saying that s is equal to 2s plus 1, which means that negative s is equal to 1 and s is equal to negative 1. This is clearly absurd because we attempted to solve for something that didn't exist in the first place. So when you do that, you may get ridiculous answers. Only try to solve for things after you're sure they actually exist. All right, now one last thing is the harmonic series. And another typo here, I didn't really edit these too well. Right, that's from the LaTeX code that I use to create things. FRAC actually creates a fraction. So this series here is called the harmonic series. It's the summation as k goes from 1 to infinity of 1 over k. You should know this by name. If someone just says the harmonic series, you should know it's the name for this thing. And now I'm going to show you that this one diverges. So here's the idea. If it converged, converging means that the partial sums get closer and closer and closer to the correct answer. But that's not going to happen. I can explain to you that we will never be within 1/2 of the correct answer. Because let's notice. I have 2 fractions here. This one is 1/4, and this one is bigger than 1/4. So that total is bigger than 1/4 plus 1/4, which is 1/2. So when I add these together, it's more than 1/2. Now, what if I look at the next 4 terms? 1/5 is greater than 1/8. 1/6 is greater than 1/8. 1/7 is greater than 1/8, and this is 1/8. So these 4 things added together are definitely bigger than 1/8 plus 1/8 plus 1/8 plus 1/8, which is 1/2. And I can keep doing that. If I add together these 2 terms, the total is more than 1/2. And then if I add together the next 4 terms, that's bigger than 1/2. The next 8 terms, up through 16, that's bigger than 1/2. and it would keep going forever. If this is convergent, it means that these partial sums are approaching something. But they're not approaching something, because if I keep going, it's always getting bigger by a discernible amount. This is not asymptotic. It grows by a half, 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 it grows by a half. That's growing infinitely large. So what you should know here is, one fact is that you should know the harmonic series by name, and you should simply know that it diverges. That is a well-known fact. You can just assert it when you need it. Hopefully you understood that explanation. I'll show you another one later on. But it is just worth knowing that the harmonic series is a very famous example of something that is not geometric and has a bunch of tiny terms, but it is divergent. Okay, that's it.